Hello everybody, let's begin with question 9. Now two objects are being pulled along a smooth floor by a 60 Newton force, smooth meaning no friction. Object A is 14 kilograms and object B is 6 kilograms. Now, the masses do not slide against each other because the masses are sticky and they stick to each other. Now calculate the force of object A friction experiences due to object B. Now, for this question, the concept to be used is the concept of a system boundary. Now, what's a system boundary? A system boundary is drawn around different objects to decide which forces are internal and which forces are external. Now, when we change the system boundary, we are able to turn an external force into an internal force and vice versa. This is going to help us solve the problems. Now, the first thing that we got to do, right, usually in this question is to draw a boundary that comprises two objects. So when we draw a system boundary around the two objects, then A and B becomes a single object. So then we can write down as the answer, considering A and B as a system. Then what we can do is that we can write down F net equals to MA. Right. So now there's a and B is a single object. So this is a single object A and B being pulled along by a 60 Newton force. Okay. So this object A and B is 20 kg. So this means that, okay, 60 is equals to 20A. So A is equals to 3. This means that both objects have an acceleration of 3 meters per second squared. Now, let's take a look at the second part of the problem. Now that we've drawn a system boundary around A and B, it is possible to draw a system boundary only around B alone. So if we draw a system boundary around B only, this is B, it's 6 kilograms. Now then, let's talk about the forces acting on B. You know that the acceleration of B is 3 meters per second squared to the right. Okay, so the acceleration of B is 3 meters per second squared to the right. Right, so what must be the force acting on B? The force acting on B must be to the right as well. So we call this friction. So the answer can be obtained by changing our system boundary to considering only B as the system. Now, if we consider only B as a system, then F is equals to 6 times 3, right? So that gives us F equals to 18, which means that the friction force is 18 newtons to the right. Okay, but that's not the answer. The answer is calculate the force that object A experiences due to object B. Then over here, then now we can write due to Newton's third law, right? Since object B experiences, since the friction force by object A on object B is 18 Newton to the right, thus the friction force by object B on object A is 18 Newton to the left. And that will be your final answer. So let's take a look at how our method that using system boundaries is different from the method that's listed in the tutorial. Okay, for in the tutorial, they start off with, well, it's actually the same because they use a system of total mass, okay, A and B, to obtain an acceleration of 3, and then after that, they get friction of 18 newtons. However, they didn't write these important lines, which are considering A and B as a system and considering only B as the system. Okay, so this is how you do question 9. All right, let's take a look at question 10. Here we have two cars, A and B, and one is, both of them are the same mass of 1000 kg, but one of them has got more resistance force and one of them has less resistance force. So let's draw in all of the forces acting on both the objects. Okay, so here's A and B, They are both 1000 kg, and then one of them has a resistance force acting, and the resistance force is 1250 newtons, because it is a quarter of 5000 newtons. And then the other resistance force is 3250 newtons. Okay, wait. So the other resistance force on car A is 3750 newtons. Now for part A, the objects are moving at constant velocity. Constant velocity. Alright, so we need to figure out what is the force exerted on car A by the tow bar. Now, so we want to find out what's the force in the tow bar. And one easy way to do that is to draw a system boundary only around B. Okay, so we can write considering B as the system. Alright, so if we write considering B as the system, then we will get this kind of drawing over here. There will be 1250 newtons resistant force and T. So if considering B as a system, T will be equals to 1250 newtons. Okay, so if T to the left is 1250 newtons, okay, thus the force of the tow bar on A is tow bar on A is 1250 newton to the right. Okay, because on A, the tow bar on A is pulling in this direction. It is a tension after all, right? Okay, so that's the answer for part A. Now for part B is slightly more challenging. For part B, the cars move with a constant acceleration of 2 meters per second squared. So let's take a look at the system here. Okay, A and B. Now we assume that the resistance forces are still acting the same amount, I guess, since there's no other information given. Okay, then here we have the acceleration is 2 meters per second to the left, 2 meters per second. We assume that the acceleration is to the left as well. Okay, now what is the force exerted on car A by the tow bar? It's really easy to do this question again. So now we consider B as a system again. Okay, so consider B as the system. Now, as we consider B as a system, then there'll be two forces acting on B, the 1250 and T, and B is accelerating at 2 meters per second squared. So we can write that E minus 1250 is equals to the mass of B multiplied by 2. And this is going to give us T is equals to 3250 newtons. So if T is equal to 30250 newtons, so thus the force on the tow bar on A, so the force of the tow bar on A is 3250 newton to the right. Okay, I'll move this up so that you can see it. Okay, so this is the force of tow bar on A will be 3250 newtons to the right. Okay, so now let's take a look at car A. Let's take a look at car A. So to answer the second part, what is the driving force on car A? So we consider A as the system. Now, if we consider A as the system, then over here, okay, this is the 3750 Newton resistance force. This is the 3250 Newton tow bar force. And this is the driving force, which we can call Fd. And then over here, this is acceleration 2 meters per second squared. So as you can see, the net force is going to cause acceleration. So Fd minus 3750 minus 3250 is equals to the acceleration of A. So this gives us Fd is equals to 9,000 newtons to the left. Okay, so this is going to be what it looks like. You can consider A and B as a system alternatively. All right, so this will be question 10. So remember, the system boundary exists so that you can draw different bodies within the system boundary to make the forces internal or external forces so that you can solve them easily. This is question 10. Let's take a look at question 11. For question 11, we need to understand the concept that weighing scale does not measure the weight of an object. And what the weighing scale actually measures is normal force. So a box is placed on a weighing machine in a moving lift. Describe the motion of the box if the reading on the weighing machine is its true weight. Now I want you to circle this word reading on the weighing machine and change this word to normal. So then that way, right, we are able to understand the question a lot more easily. So let me give you an example for part A. For part A, it says that the reading on the weighing machine is its true weight. So what does that mean? That means that the normal is equals to the weight. So when the normal force is equals to the weight, then the acceleration will be equals to 0. So if the acceleration is equal to 0, then the lift is moving at constant velocity. So here's the way to deal with such questions. First, you look at the forces. Then you look at the acceleration. Then you talk about the motion. Let's do part A, part 2. Describe the motion of the lift such that the reading on the weighing machine or normal is less than the weight. So let's take a look. So the weight is here and the normal is less than the weight. So if the normal is less than the weight, then the acceleration is downwards. So that gives us the answer that the lift is accelerating downwards. Okay, now this can happen in two situations. The lift is going up but slowing down. When the lift is going up but slowing down, its acceleration is downwards. But when the lift is going down but speeding up, then the lift is also accelerating downwards. In both cases, the acceleration is downwards. Okay, now next, describe the motion of the lift such that the reading on the weighing machine or normal is 0. So let's take a look at the third case. When the reading on the weighing machine is 0, that means there is a weight, but the normal equals 0. So this only occurs when the acceleration is equals to 9.81 meters per second squared. So that means to say the box is in free fall. So I don't think it's even in the lift anymore. Maybe you took it outside and then you dropped it. So in this case, when the normal is 0, it's not touching the weighing machine, so it's in free fall. Let's take a look at question B. Question B gives us the actual reading on the weighing scale. All right, so remember, this is not the weight of the object. This is the normal force of the object. Okay, now, when the lift starts to move from rest, the sensor registers the reading over a certain time interval. Okay, so what is the actual weight of the object? Now, when the lift velocity is 0 and the velocity is 0, there are 2 points when the velocity is actually 0. I suppose this point over here is when the velocity is constant. Now, when the velocity is constant, the acceleration equals to 0. Okay? And anyway, the lift starts from rest, so over here, the acceleration also equals to 0. So let's take a look at B part 1. When the acceleration equals to 0, the normal will be equals to the weight. And let's read. So therefore, acceleration is equals to 0 when t equals to 0 and the normal equals to 98.1, which equals to the weight. So therefore, the weight is 98.1 newtons. Okay, let's take a look at number 2. Determine the acceleration of the object during the time period t1 to t2. Let's take a look at the box over here. There are two forces acting on the box. This is the weight, which is 98.1 newtons, which we know from B part 1. And this is the normal force. Now, during the time T1 to T2, the normal force is actually 82.7 newtons. So this means that the object should be accelerating downwards since the weight is larger than the normal. Now, in order to find the acceleration of the object, okay, we need to find the mass. So how do we find the mass? The mass of the object, okay, will be the weight of the object divided by g. Okay, the weight of the object divided by g. Now, the weight of the object is 98.1 and g is 9.81. So the mass is 10 kg. So actually, this box is 10 kg of mass. Okay, so it's 10 kg. So the acceleration will be the net force divided by the mass. So how do we find the net force? Very easy. The net force will be 98.1 minus 82.7, and the net force will cause the mass to accelerate. Okay, so the acceleration will therefore be 1.54 meters per second squared downwards. Now remember, acceleration is a vector, so please write the direction of the vector. So let's describe and explain the object motion during the following periods. So I just want you to remember that when we describe the velocity should be described as increasing, decreasing, or constant, the rate of change of the velocity as well. Okay, so whether the velocity is increasing, decreasing, or downwards, and the direction, and also the rate of change of velocity. So what is the velocity between period 0 and T1? Now over here, you can see that the normal force is equal to the weight. So over here, normal equals to the weight, acceleration equals to 0. Now over here, normal is less than the weight. So let me just remind to you again, the normal is less than the weight. So when the normal is less than the weight, the acceleration is downwards. Okay, so you can see the acceleration is 0 and then there's something. So we can say that the object moves from rest with downward velocity increasing at an increasing rate. That means the downwards acceleration is getting larger. Now, between T1 and T2, you can see that the same situation applies. The normal is less than the weight, so the acceleration is downwards. So the object moves with downwards velocity that is increasing at a uniform or constant rate because it's constant acceleration. Okay, now over here, the acceleration becomes 0 again. So when the acceleration becomes 0 again, the object continues to move with the downwards velocity increasing at a decreasing rate. Now notice that it is the acceleration that is decreasing and not the velocity. Okay, now what do I mean by that? The object is not slowing down. Over here, even though the acceleration is reducing, okay, from 1.54 to 0, all right, this 1.54 is 0, the object is not slowing down. In fact, the object is getting faster instead. How can an object get faster when the acceleration is decreasing? Because everywhere along this line, it is getting faster. When there is acceleration, the object will get faster. When there is no acceleration, the object will not get faster. And it's only when there is negative acceleration that the object will slow down. So there's a very common misconception that between T2 to T3 that the velocity slows down. I'm sorry, the downward velocity increases, but it is the acceleration that is decreasing. Okay, after T3, the object moves with a constant downward velocity because normal equals to the weight, so acceleration equals to 0. But please note, the object is not stopped. It is moving at the highest velocity. okay, the object is not stopped. Just because the acceleration is 0 does not mean the object is stopped. Okay, so can you please remember this? Just because the acceleration is 0 does not mean the object is stopped. Okay, so that is question 11. Let's talk about question 12. Now there's a car of mass 1500 kilograms traveling at 30 meters per second, and the driver applies the brakes so that the braking force, right, increases to a maximum and then decreases to 0 as shown. So over here, the car is moving fast, okay, at 30 meters per second. And then over here, the braking force increases. And the maximum braking force is over here, max braking force. And by the time 20 seconds has passed, the car is completely stopped. Okay, so this is what's happening in the question. Now calculate A, the momentum of a car when it's traveling at 30 meters per second. The momentum is just the force times the mass times velocity, so it's 45,000 kg meters per second. Now what is the change in momentum between t equals to 0 and t equals to 10? Now the concept for this question is that the area under the graph is the impulse, and the impulse is the change in momentum. So once again, the concept for this question is that the area under the force time graph is impulse, and impulse is equal to, or impulse causes, a change in the momentum. Okay, so the initial momentum of the car is 45,000 kilograms per meters per second. Now, from 0 to 10, let's try to find the impulse from 0 to 10. Impulse from 0 to 10 seconds will be the area under the graph. Okay, so that will be half times the base times the height. But then we don't know what is Fmax. What is Fmax? Now, in order for us to find out what is the value of the area under the graph here, we need to use the entire graph as well as what we know about the momentum. So when the car reaches to this point, after 20 seconds, the car is stopped. Now, if the car is stopped, that means the momentum that is lost is the entire momentum of the car is lost. So this entire area is 45,000, okay, kilograms meters per second. So what happens here is that the entire area from 0 to 20 seconds is equal in magnitude to the momentum of the car, since the car comes to a stop. So therefore, the area from 0 to 10 seconds is half of the total momentum of the car in terms of magnitude. Of course, it has to be negative in sign. So therefore, that means that the area on the left half of the car will be 22.5 thousand kilograms per meters per second. So let's take a look. What is the change in momentum from 0 to 10? Therefore, the change in momentum from 0 to 10 will be negative 22.5 thousand kilograms meters per second, since the car is slowing down. Okay, so for time period t, if you take a look at the official solution, all right, the change of momentum will be minus 45,000. Okay, so then the change of momentum for t to 0 will be negative 22.5 thousand. Okay, what's the kinetic energy at t equals to 0 and t equals to 10? So we need to find out what is the car's speed at t equals to 10. Now, at time t equals to 10, what is the car's velocity? Car's momentum is equals to 45,000 minus 22,500, which equals to 22,500 kilograms meters per second. All right, now, so then the car's velocity, car's speed will be equals to, okay, 5,000 divided by the mass of the car, which will give us 22.5 meters per second. So what we can do now is that we can actually work out the kinetic energy, okay, at initial kinetic energy and final kinetic energy. So initial KE at T equals to 0 is equals to half m v squared, and the v will be 30 squared. Wait a minute, this car is 1500. Oops, let me just change these values. So the speed of the car will be 22,500 divided by 1500. It will be 15 meters per second. So the initial KE at T equals to 0 will be half 1500 times 30 squared. This will be 6.75 times 10 to the power of 5 joules. And then the KE at T is equals to 10 will then be equals to half m and v squared, 15 squared. This will be equals to 1.69 times 10 to the power of 5 joules. Okay, all right. So that is the simple method to do it. However, there is a cheat code. The cheat code is an easy way of calculating kinetic energy. Kinetic energy is the momentum squared divided by twice the mass. Okay, so an easy way to calculate the momentum squared divided by mass is 22,500 squared divided by 1,500 times 2. And that will also give you the same value as before. Now, why is the kinetic energy equals to the momentum squared divided by 2 times the mass? The reason is as follows. Okay, now kinetic energy is let's talk about momentum. Momentum is mv. Now, let's square it. Okay, so momentum squared will be m squared v squared. And then let's divide it by m. So that will be mv squared. And then let's multiply it by half. So half, or rather t squared over 2m will be half mv squared. Ta-da! So kinetic energy is equals to momentum squared divided by twice the mass. This is a very useful relation, okay, that you need to know for nuclear physics later on. Okay, so we are done with question C. Okay, so now we know that the kinetic energy has decreased, okay, to 1.69 times 10 to the 5 joules. Let's take a look at question D. What is the value of F max? Now, remember we said that the value of F max over here, the change of momentum is 45,000, and the base is 0 to 20 and F max. So very clearly the area under the graph, okay, is half base times height, and that is equals to 45,000. And so it's not difficult to determine that F max is equals to 4,500 newtons. Okay, so what's the maximum deceleration of the car? The maximum deceleration of the car is the maximum force divided by the mass. So the car's maximum deceleration is 3 meters per second squared. Okay, finally, sketch the acceleration time graph and velocity time graph of the car. Now, the acceleration time graph is exactly the same as the force time graph. How come? Let's take a look. All right, so here's the force and time. Now, how do we get acceleration? Acceleration is force divided by the mass. So what happens if we divide this whole graph by m? So I guess the graph will shrink a bit, okay? The graph will shrink a bit, but now this will be the acceleration graph. Acceleration graph will be simply the ft graph divided by m. Now, what about the velocity time graph? Now, the velocity time graph is a little bit more difficult to draw. Okay, the velocity time graph will be drawn like this. Okay, Now, initially, the car is moving very fast. It's moving at 30 meters per second. And then we know that sometime in the future, it comes to a stop. So that's 0 meters per second. We'll put a meters per second on the top so that we don't have to keep writing meters per second. Okay, so we know that sometime in the future, it will reach 0 meters per second over here. And we know that sometime halfway down, it's going to reach 15 meters per second because that was what we worked out. Okay, the time is 20, the time is 10. Now, how are we going to connect all of them? Okay, let's take a look at the graph over here. This acceleration graph here says that its acceleration is equal to 0. This one here says that the acceleration is the maximum deceleration. And this one over here, it says that the acceleration equals to 0 again. Now, when we talk about acceleration equals to 0, there is no change in v. So when the acceleration is equal to 0, the vt graph has a horizontal gradient. So that means to say at a equals to 0, when the time equals to 0, the acceleration is 0, the velocity graph gradient should be straight. And over here, at time t equals to 20, the velocity graph gradient should also be straight. Now, what happens when the acceleration is -3 at t equals to 10? That means that the velocity is decreasing. Okay, if the velocity is decreasing, then the gradient should look like this. The velocity is decreasing, isn't it? So what we have here is that we need to follow the gradients, okay? So it will be a S-shaped graph. Oops, my gradient is not very good. Okay, so it's an S-shaped graph. All right, the acceleration here is equal to 0. The acceleration here is -3. And the acceleration here is 0 again. So this is how you draw the velocity time graph. And that is the end of question 11. 12.